There are fast reactions, such as the combustion of alcohol and the burning of magnesium, as you can see over here. And there are also slow reactions, such as the rusting of iron, which takes almost 2 years for any significant reaction to start occurring. Welcome to reaction rates. So this section is looking at why some reactions are faster or slower than other reactions. And the reason why, or the way that we look at how reactions work and the factors that affect reaction rates is modeled by this thing called collision theory. We met collision theory back in when we were looking at thermochemistry, but just as a recap, collision theory was a chemical postulate or a way of modeling how reactions work. It had three kind of ideas. The idea was that reactions and reactants existed as particles like this, and they're all bouncing around in random motion. And when a reaction occurs, these particles had to first collide. They also had to collide with enough energy to break the bonds of the reactants. So they had to collide with energy that was greater than the activation energy. And lastly, they had to collide in the correct orientation. So the idea is this: when particles collide with energy greater than the activation energy and also collide in the correct orientation, we call these types of collisions successful collisions. So sometimes you'll see in the literature these are being called as other things, such as fruitful collisions, energetic collisions, and so on. But for our purposes, we'll use successful, and I think this is the most common one that you'll see in your textbooks. So a successful collision is a collision that meets all these three criteria. It first collides with enough energy to break the bonds, and that means energy that is greater than activation energy, as well as collide in the correct orientation. So when this happens, we get a successful collision, which means a reaction occurs. When collisions occur, but they don't meet these criteria, or when particles don't collide, we don't get a successful collision and the reaction does not occur. Instead, the reactant particles just bounce into each other and then bounce away. So why is collision theory used as a way of measuring reaction rate? Well, the idea is the more successful collisions we can get per second. So over here, I'm just going to write in black. If we get an increase in the number of successful collisions per second or per unit time, so you can use per second or we can say per unit time, right? What will happen is that the rate of reaction will be faster. But if we have a decrease in the number of successful collisions per unit time, then that means that the reaction will be slower. Okay, so now that we've established that if we increase the number of successful collisions per unit time, then the reaction is faster rate of reaction. So the question now becomes, what are the factors that will increase the rate of reaction? That is, what are the factors that will increase the number of successful collisions per unit time? And those factors are going to be things such as concentration. They're going to be things such as pressure, if you're talking about gases. They're going to be things such as surface area, if we're talking about solids. And they're going to be things such as temperature and a catalyst. Okay, so all these things, when we change these things, they will affect the rate of reaction by affecting the number of collisions per unit time, and the number of successful collisions per unit time, sorry. So the focus of this section is being able to generate a response and an answer as to why the concentration might change the rate of reaction, or why the surface area might change the rate of reaction, and being able to provide a written response to each of those questions. Okay, so the first one is going to be concentration. If we have a low concentration container, such as the one on the left, and compare it to the high concentration container, such as the one on the right, what do we see? Well, the difference really between the two of these is that with concentration, the concentration means what? It means the number of particles per unit volume has increased in the higher concentration container compared to the lower concentration container. So over here we can see that if we have an increase in concentration, what that means is that there's an increase in the number of particles per unit volume, right? So per unit volume just means any volume, so per liter, per milliliter. So let's say, for example, these are 1 liter containers. They might not actually be 1 liter containers, but for example, they are. We can see here that in the low concentration, there's a few particles per liter, and in the high concentration container, there's a lot of particles per liter. So increase in concentration means increase in the number of particles per unit volume, which means that more particles collide per unit time. Okay, and if more particles collide per unit time, there's going to be more successful collisions per unit time. Okay, and if there's more successful collisions per unit time, that will increase the rate of reaction. Okay, so concentration essentially follows this explanation here. Okay, cool. So the second thing that we're looking at here is catalysts. So catalysts are what? Catalysts are things that speed up the reaction. In your definition of catalyst, you need to have 3 points. 1, the catalyst is a substance, a chemical substance that increases the rate of reaction. The way it does it is by providing an alternative reaction pathway. Right? And this alternative reaction pathway has a lower activation energy than the original reaction pathway, and that results in an increase in rate of reaction. We also must make sure to note that the catalysts are not used up in the reaction, so they are not consumed by the reaction. Okay, so these 4 points must be in your definition of catalyst. They increase the rate of reaction, provide an alternative reaction pathway that has a lower activation energy, and are not consumed by the reaction. So just a brief note, what is an alternative reaction pathway? The idea is this: if the overall reaction is A forms, let's say, D, right? That might have a really high activation energy. So there's a lot of energy required to break the bonds. So therefore, very few particles will have enough energy to break the bonds. But if we have a catalyst, it might be A to B, and then B is converted to C, and then C is converted to D using the catalyst. So the catalyst would facilitate these intermediate reactions, right? Such as A to B, B to C, C to D. And each of these intermediate reactions might only have a very low activation energy. So a lower activation energy like this. So more particles would have enough energy more particles would have energy that's greater than the activation energy, meaning that more particles have the ability to break bonds. And as a result, there'll be more successful collisions and a faster rate of reaction. So let's look at the explanation of how to tackle catalysts. Okay, to explain this concept, let's have a look at the idea behind the, let's say, entry requirements for Monash medicine. So Monash medicine requires 3 things. We've got the UMAT over here, we've got the prerequisite studies, ATAR, and then we've got an interview. Okay, let's say the entry requirement for Monash medicine was a 99 ATAR, right? So what does that mean? If we take a look at the spread of ATARs in the in schools, let's say, for example, it was distributed like this, right? So like, let's say, I know it's not, but let's say, for example, a small number of people here get above 99, and then a certain amount of people here get above 50, and then a certain number of people get above 25, and so on. So you can see here that if it was normally distributed, let's say this is the number of people, we got a distribution like this, and this was the ATAR here. Okay, what we would see is that if the cutoff for Monash Med was above 99, then on this graph, the people who would get in or who would meet that requirement are here, right? So these are the successful applicants. Successful applicants here, right? So, and this line here is the cutoff. So I'm just going to go and change the color and change the color over here, and let's make it black. Yeah, let's say this line here represented the cutoff. Okay, so what happens is this: if I were to change the ATAR to something like a 90 ATAR, or let's make it more dramatic. Let's make it a 75 ATAR. Okay, so if so ATAR. So let's say I have a 75 ATAR cutoff for Monash Medicine. For some reason, they decided to lower the cutoff. What happens? So this requirement goes this way. So all of a sudden, our new entry requirements are here, right? At the 75 ATAR mark, which means all of a sudden, it's not only the people in this section here that are able to get into Monash Med. Instead, all these people here who have the 75 ATAR and above are now able to become successful applicants. Okay, so what we've done is we've lowered the entry requirements into medicine. Now, why is this significant? Well, like, how does this relate? Well, the same idea happens with our catalysts. That is that we have energy distributed on a curve, right? And this is called like a Maxwell-Boltzmann curve. And what this basically represents is on the y-axis, we have the number of particles. And on the x-axis, we have the energy of the particles. And normally, the energy of the particles is normally distributed, something like this, okay? And then there's a mark here. So this might be like 500 kilojoules or 20 kilojoules, I don't know, for the activation energy, something like this, okay? So what this means is normally only this section over here, only a small proportion of particles will have energy that is equal to or greater than the activation energy. So only some of these will be successful collisions or successful particles with enough energy to break the reactant bonds. So when we have a catalyst, what happens is that this activation energy requirement goes down. So this is the activation energy here, except with the catalyst. Okay, and what that means is that when we add the catalyst, all of these particles here now have enough energy to break the reactant bonds. So there's going to be a greater proportion of particles with energy enough to break bonds, and therefore greater proportion of particles will have successful collisions. So the way that we answer this is, if they ask you, how does a catalyst work to increase the rate of reaction? You say, you first of all will define the catalyst. So we define the catalyst, something that increases something that increases the rate of reaction without being used up by providing an alternative reaction pathway with a lower activation energy. What this means is that it increases the proportion. So what it does is that it reduces the activation energy. So basically, it increases the proportion of particles with energy that is equal to or greater than the activation energy. Okay, as a result, there's going to be a greater proportion of all collisions will be successful collisions. Remember, in order for a successful collision to occur, we need to have our energy. We have to have collision. Energy must be greater than activation energy and correct orientation. So when more particles have energy greater than activation energy or greater than or equal to activation energy, we get more successful collisions. Therefore, with an increase in the proportion of successful collisions, we get an increase in the number of successful collisions per unit time. and therefore an increase in the rate of reaction there. Okay, so that's your definition, that's your explanation for catalysts. Okay, so the last section is looking at temperature. So how does temperature increase the reaction rate? The idea is this: when we increase temperature, what we're doing is we're increasing the average kinetic energy of all particles. What that means is this. Remember, we had this energy distribution curve where on the y-axis we've got the number of particles, and on the left axis, on the x-axis, we have the energy, right? The kinetic energy of the particles. So when we increase the temperature, what happens is we increase the average kinetic energy of all particles. So what that means is that this thing here, remember this is known as a Maxwell-Boltzmann distribution. So it literally just says that, like if I look at the level of energy, if the level of energy is medium, there's a big number of particles that have a medium level energy. But as I go up to like a high level of energy, there's a small number of particles. So let's say a bottle of water, let's say this is some water, it just means that there's a small proportion of these particles which are moving really fast, a small proportion of particles with a high level of energy, a small proportion of particles with low level of energy, and a big proportion of particles with a medium level of energy. That's all it's saying, right? And that the average kinetic energy is the temperature, and it could be something like 25 degrees Celsius. Okay, so when I increase the temperature, what happens is that I go from this distribution here in black to a distribution like this, for example. Okay, well, this is probably not the best example. We can see that there's a picture off the internet here that you can see the cold one has it shifted to the left, and the hot one has the curve shifted to the right. Total area under the curve is the same because the number of particles is the same, but we can see that in let's say the blue one over here, more of them have higher levels of energy. What does this mean in terms of my reaction rate? Well, if we take a look at the activation energy, let's say this is the activation energy over here. So EACT here. In the cold black one, so the black one was, let's say, a low temperature, and the blue one here is a high temperature. Well, in the black one, what we see is that we have these number of particles with energy equal to or greater than the activation energy. But when we increase the temperature to the high temperature, we see we've increased the amount of energy that each of these particles have, and basically the proportion of all the particles that have energy greater than or equal to the activation energy is higher, which means that more particles here are going to be successful. So this is like basically, remember our previous analogy about the 99 ATAR for med. This is like, instead of having instead of like, let's say 400 people getting an ATAR above 99, what happens this time is that 800 people get an ATAR above 99. So we're just making the people more smart so they're able to pass the requirement. Here, instead of saying that we're lowering the energy requirement for a successful collision, what we're saying is that more particles now have energy that is greater than the successful collision. Than the requirement for successful collision. So in order to recap, what we'll do is we'll describe what the explanation was for temperature. So the first point was that temperature would increase the average kinetic energy of all particles. And then that results in what? In a greater proportion of particles with energy equal to or greater than the activation energy. And that would result in what? A greater number of successful collisions per second or per unit time. So I'll write unit time here, and therefore that increases the rate of reaction. But we must also remember that temperature does another thing. So what am I saying here? I'm saying that there's two explanations for temperature, and when you're writing your responses in the exam or the SACs, you must remember to include both of these explanations. So what are these explanations? So what's the second explanation? Second explanation is that temperature also increases the speed of the particles. Okay, so kinetic energy is the energy of motion, but that takes into account the mass of the particles. Okay, so which is different from just literally just the speed of the particles. So the second explanation that you need to remember is this. When we increase temperature, we also increase the speed of motion of particles. Okay, which is separate from the kinetic energy of particles. And what that does is that will increase the number of collisions per second. So in other words, it will increase the frequency per unit time. So I'll say unit time just to be fancy. All right, and then therefore that results in what? An increase number of successful collisions. So it increases the number of collisions per second. Therefore, it increases the number of successful collisions per second or per unit time. And then that results in what? An increase in rate of reaction. So we need to remember that both 1 and 2 play a role in increasing the rate of reaction. We also must remember that the majority of the increase in the rate of reaction when we increase the temperature is due to number 1. So number 1, the increase in the average kinetic energy of all particles, that has a more significant impact on the rate of reaction than number 2. So I'll just write here is more important. Okay? And they have tested this fact in the past. Cool. Well, that concludes our section on rate of reaction.